Question 4. Colourless solutions of X aqueous and Y aqueous rectiform an orange solution of Z aqueous. Blah 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 blah. Reduce the amounts of X aqueous and Y aqueous at equilibrium. For this question 4, I'm going to skip question 4.2. I'm not sure how to do it, and it's a graph question as well, and it's 3 marks, so it's not going to be that simple. But I'll carry on with the rest of it. That's letting you guys know before I carry on. So I like to use this method. If you guys been watching this whole playlist, the ICE method, and what you want to do on the top is what you're working with. So in this case, we're working with X, Y, and Z. I stands for initial moles, C stands for change in moles, E stands for equilibrium moles. Now that we're on the same page, so X contains initially 0.50 moles of this. How do I know it's initially? Well, it doesn't tell me that those moles were at equilibrium. It doesn't tell me that. It also tells me 0.50 moles of Y. And it then tells me that at equilibrium of Z was 0.20. However, it doesn't tell me the initial moles of Z, so we're going to assume it's 0. So the change in moles is plus 0.20. Therefore, if we're adding 0.2 moles, we're going to do minus in this side. It's going to be minus 0.20, 0.30. And for Y, we're not going to minus 0.20 because it's a 2 to 1 molar ratio. We're going to minus 0.20 times by 2, 0.40. That will give me 0.10. So the amount of moles of X is 0.30, Y is 0.10. Got to get rid of it so I can put it in the box. 0.30, 0.10. And that is the equilibrium moles. 0.10. I'd really recommend to learn that method because it's a really reliable method. And then skipping 4.2, 4.3, student prepared another equilibrium mixture in which the equilibrium concentrations of X and Z were X is aqueous 0.4 moles per dm minus cube, Z aqueous 0.35 moles per dm minus cube. For this reaction, the equilibrium constant Kc is that. Calculate value for concentration of Y. Give your answer to appropriate number of significant figures. So let's construct the Kc equation. Kc, remember Kc equals square brackets. That's what I would immediately draw out, square brackets, so I don't get confused between Kc and Kp. So Kc is square brackets, products over reactants. So products in this case is Z over the reactants X and Y. X and Y. However, Y, there's 2 moles of Y, so therefore it's going to be squared. What are we trying to find? We're trying to find the concentration of Y, so we need to rearrange it. So you get Y squared equals Z divided by X times by Kc. What we do is times by X times by Y squared, and Y squared is equal to Z divided by Kc, or divided by Kc times by X. Now what we can do is just substitute values in. So Y squared equals what we're working with, the concentration of Z 0.35. It tells in the question no equilibrium concentrations, so the other concentration 0.35 over X equilibrium concentration 0.40 times by Kc 2.9. So I get Y squared is 0.35 over 0.40 times by 2.9. I get Y squared concentration, equilibrium concentration of Y squared is 0.3017, etc, etc. So now we need to square root it, and I get Y is equal to, you have to show these steps as well, otherwise it will reduce some marks for not showing the method. So 0.549, which is 0.55, just round it to 2 decimal places. And then 4.4, the student added a few drops of y to the equilibrium mixture of x aqueous, y aqueous, and z aqueous. In question 4.3, suggest how the colour of the mixture changed, give a reason for your answer. So these type of questions, where it's like, does the colour change? Well, it's saying, suggest how the colour changed, give a reason for your answer. You have to think really like in detail. So, the student added a few drops of y to the equilibrium mixture of x, y, and z. So, let's look at the equation again. Well, first things first, what is delta H? Delta H is negative, so that tells me the forward reaction is exothermic, backwards reaction is endothermic. We might need that, we might not, I don't think we will. Anyway, so we're adding more concentration of y, we're adding more drops of y, a few drops of y. So what's going to happen is equilibrium is going to oppose it. Le Chatelier's principle, when equilibrium is in its standard conditions, is try to oppose change, temperature, pressure, or something like that. So if we're adding drops of y, what's going to happen to equilibrium? Well, it's going to shift to the opposite side. So it's going to shift to the right hand side to oppose the increased concentration of y, to actually decrease the concentration of y. And therefore, what's going to happen to colour? Well, we know colour solution of x, y reactive form or orange solution of z. So therefore, we're going to have more. We're going to have more of z. So therefore, it's going to become more orange. Okay, so the colour of the solution changed. Well, it's not going to be orange. We already know z is orange. It's going to become more orange because we're going to have more drops of z, or a higher concentration of z. So more orange. Reason: equilibrium moves to right hand side slash forward direction slash exothermic direction, because you know delta H is negative. Don't need to really include exothermic direction because this is about just equilibrium, not increasing temperature, adding a few more drops. And why does it do this? Well, it does this to oppose the increased concentration of y, hence to decrease concentration of y. Actually, we don't really need to include this part. Okay, and then 4.5, the student warmed the equilibrium mixture from question 4.3. Predict the colour change, if any, when the equilibrium mixture was warmed. Again, a very tricky question. It requires, it's not just one step, it requires multiple steps. So student warmed the equilibrium mixture. Well, first thing, when I was attempting 4.4, I labeled that the forward reaction is exothermic, and we're going to need it now because I know delta H is negative, forward reaction is exothermic. So if what are we doing? Well, we're warming the equilibrium mixture. So what does that mean? We're increasing the temperature. If we're increasing the temperature, equilibrium is going to shift to, well, the forward reaction is exothermic, we're increasing the temperature, so the equilibrium is going to shift in the opposite direction, the endothermic direction, because it wants to decrease the temperature. And exothermic reaction will increase temperature, but equilibrium won't do that. It will shift to the backwards reaction, the left hand side, to decrease the temperature. So what's going to happen to the colour change? Well, we know the right hand side becomes more orange. The left hand side, well, are colourless solutions. That doesn't mean it's going to immediately become colourless. It just means that the orange colour that we have of Z is gonna fade in color. So the orange color would fade in. And if the temperature is decreased, like the student cooled the equilibrium mixture or made it put in a whatever, the temperature decreased, well then it would shift to the right hand side exothermic direction to increase the temperature, and therefore the color change would be more orange to form Z, which is orange solution, become more orange. But in this case it's not. It's going to go to the left hand side endothermic direction, the backwards direction, and the orange color would fade in, because remember X and Y are colorless solutions, so the orange plus the colorless, the orange color would fade in. And that is the end of question 4 except for 4.2.